Hi everyone, this is the video lesson of 5.2, the derivative of the general exponential function y equal to e to the power of x, part 2. So if you haven't watched the first part yet, please go back and watch this. We've talked about the warm-up, example number 1, a, b, c, and d. Let's continue. Example number 2. Determine the equation of the line tangent to y equal to 5 to the power of x, where x equals to 1. So step 1, you have to find the general slope. So if you have y equal to 5 to the power of x, the derivative, y prime, is going to be 5 to the power of x times ln of the base, which is ln 5 in this case. The goal is to find the slope here. So for x equal to 1, the slope equals to y prime of 1, which equals to 5 to the power of 1 times ln of 5. And if you leave this in exact form, you can write down m equals to 5 times ln of 5. Just like that. Again, once you find the slope, you have to find the point before you can find the equation. So if you go back to the fact that x equals to 1, you got to plug it back in, which means y of 1 will give you 5 to the power of 1. So y equals to 5. So this implies that the coordinate x, y equals to 1, 5. Again, once you have the point and you have the slope, you can now find the equation of the line. So there are two ways of doing this. One method is to start with y equal to mx plus b. And again, in this case, you're given the fact that x is going to be 1, y is going to be 5. The slope is going to be 5 ln 5. To solve for b in exact form, b equals to 5 minus 5 times ln of 5. If you plug it back in, therefore, y equals to the slope, which is 5 ln 5 times x, plus b, which in this case is 5 minus 5 ln of 5. And again, that's one form in terms of the final answer. The other form is to rewrite this in standard form. And standard form just means bring everything to one side, set it to 0, make sure that the values of a, b, and c, or a has to be positive, and the values of a, b, and c cannot be a fraction, it cannot be a decimal. So if you bring everything to the right, this will give you 5 ln 5 times x minus y plus 5 times, or 5 minus 5 times ln of 5, or the third option, and again, some students would put this in factor form, some teachers may expect this in factor form. So that last part is a common factor 5 you can bring to the front. But again, either case should be fine. So again, there's the standard form along the two different cases, just like that. One more example. Example number 3. This is from your textbook on page 240, number 8. Determining the equation of the tangent to the curve y equal to 2 to the power of negative x squared at the point on the curve where x is 0. Graph the curve and the tangent at this point. So again, press pause, spend 5 minutes, try this. Draw a diagram, go through all the steps, and when you press play again, I'll be right here and we'll take it up step by step by step. Okay, here we go. Now, before we start graphing this, and again, we'll leave a little space here just for the graph. Let's set up a scale. The first thing you want to think about is the symmetry, which will help you in terms of any reflection or anything that's symmetric about the origin. Now, the scale I'm going to use should be enough in terms of the major points of the graph. So let's say this is -2, -1, 0, 1, and 2. You go up to 1. Now, if we really look at the function y equals to 2 to the power of negative x squared. By inspection, you can tell this is going to be an even function. And again, in case you want to verify this, of course, you could plug in negative x and show that this is 2 to the power of negative, in brackets, negative x squared, which ultimately is 2 to the power of negative x squared, which is the same as f of x. And the fact that f of negative x equals to f of x, this verifies that the function is going to be even. And that's important because this means when you graph only half of this, let's say the left hand side or the right hand side, there's a reflection with respect to the y-axis, and we'll confirm this at the end. Now again, determine the equation of the tangent at the point x equal to 0. So if you find the derivative, so again, y equals to 2 to the power of negative x squared, y prime equals to, again, there are 3 steps here. Step 1, you copy this. Step 2, multiply by the ln of the base. And the third step is to multiply by the derivative, which is negative 2x. To find critical points, you set this to 0. You can express this as a fraction. That's negative 2 ln 2 times x divided by 2 to the power of x squared. Now, if you put a line in the middle, separate this as 2 different columns. If you focus on the top, you can tell that there's one value of x, and that's going to be x equal to 0. Again, form the habit of finding the location and not just the x value. And if you plug 0 back to the original function, you can tell that when x is 0, the corresponding y value is going to be 1. So 0, 1 is going to be the critical point. And I think it's going to be a maximum, which we'll verify in a moment. Now ideally, you also want to find out what happens when f prime does not exist, or when it's undefined. And in this case, you can set the denominator to be 0, but again, this is not possible. There are no solutions here, and this just means there's no critical point you can extract from the second case. Now again, if you want to find out whether the critical point is a max or min, you can go through the first derivative test or the second derivative test. It's up to you. But if I just go through increasing, decreasing, here's what happens. I know the anchor point is going to be 0 because that's the critical point. When you plug in numbers, that's negative and positive, and again, you're plugging it back into f prime, and f prime is right here. So if you plug it back into here, you would discover in the first case, the function is increasing, and when you plug it back into the second case, when it's positive, that's going to be decreasing. So this would tell you that the critical point, 0, 1, is going to be a maximum. And again, this is from the first derivative test. The fact that it's increasing, then it decreases. Now, if you keep going, your goal is to find the equation of this line, and for x equal to 0, the corresponding slope, that's going to be y prime of 0, and that's going to give you negative 2 ln 2 times 0 divided by 2 to the power of 0 to the power of 2, which really means the slope is going to be 0. And again, this is important. Don't forget, if the slope is 0, this really means graphically you're thinking about a horizontal line. And again, this should not be a surprise. It's the maximum, so that should be a horizontal line. Since the location is going to be at 0, 1, this tells you it's going to be y equal to 1. Or, if you put this in standard form, it's going to be y minus 1, which equals to 0. Now, if you put all of this together back to the graph, what you'll discover is this. There's the maximum, and it's located at 0, 1. If you draw the horizontal line, this is going to be at y equal to 1, and again, you can draw some arrows like that. Now again, the graph is going to be an even function. You can look at the domain, vertical asymptotes, but again, if I just write this down in terms of the basic details using the algorithm, domain is going to be x as an element of real numbers. If you think about the asymptotes, vertical, horizontal, and oblique, you would discover that there are no vertical asymptotes. There is a horizontal asymptote at y equal to 0, which implies there'll be no oblique asymptotes, and the asymptote's going to be right here. Don't forget to label this, and again, as you keep going, you discover that it decreases like that, and on the other side it'll be like that. Now again, we didn't go through the entire algorithm. We didn't talk about concavity, inflection points, and so on, but the question was graph the curve and the tangent at this point, and that's exactly what we did. And that's how you do example number 3. So again, spend some time, practice number 1 to 9 on page 240. Your math skills can only be as good as your last set of math homework. So until next time, all the best, and I hope this makes sense.